Hey guys, hope you're doing well. In lieu of us meeting together, I'm going to go ahead and talk about our next topic, which we talked about a little bit on Thursday before I left, but we're going to get into a little bit more, okay? And this topic can be a little difficult at times, so if you have questions, we'll answer those when we see each other tomorrow on Tuesday. All right? So, on Thursday, we did kind of a little introductory to nuclear chemistry and what that was. Whether your feelings going into are positive or negative, we got a little bit into it and saw that there are positive things about nuclear chemistry and also negative things. Some of it is media portrayed and some of it is actually true. So let's get into what nuclear chemistry is. Okay, so what we're going to look at today are a couple things. One, we're going to understand what does the word radioactivity mean. And then two, what we're going to look at in the terms of radioactivity, what are some radiations that can occur from an unstable nucleus? So the three types of radiation we're going to look at are nuclear decay is going to be alpha, beta, and gamma. All right, and we're going to see what they're all about. So let's look at radioactivity. So radioactivity, by definition, is the process by which nuclei emit particles and rays. Okay, so particles, it can travel as a wave, whatever that may be. But that's what happens, all right? And so the symbol up here on the right, you've probably seen it before watching movies or seen it in documentaries of some sort. That is kind of the symbol for radioactivity. So if you see that symbol from a chemistry perspective, that's telling you that whatever this is inside this container, inside this building, is radioactive or has the ability to be radioactive, okay? And so when these rays or particles are emitted from the nucleus, we call those terms collectively radiation, okay? So that's radioactivity. It's basically when the nucleus is emitting radiation. So remember, the nucleus is the protons, neutrons. Around the nucleus, you have the electrons that are flying around, okay? But in the side of the nucleus, you have protons, neutrons that are bound, okay? So the question you should be thinking about right now is, why does something become radioactive? Why in the heck does it? What causes it to be radioactive? There has to be something. And there is, okay? When you look at the periodic table, and we were calculating protons, neutrons, electrons, oftentimes when we were taking the atomic number and minus it from the atomic mass, neutron number was very close to proton number. And so they usually were close in ratio. However, when you get to certain elements on the periodic table, all right, they become unstable. What I mean by that is you have way too many neutrons in the nucleus, okay? And this usually happens after around potassium. Not always, but usually things start getting radioactive but beyond potassium. And we're going to see a picture of the periodic table here in a second that shows you potential elements that are radioactive. So basically, in a nutshell, why do elements become unstable? Is because they have way too many neutrons in the nucleus. Way too many. It's too crowded. And what happens is the atom will start to try to become stable, and when it becomes stable, it releases radiation in that process, and it goes through something we call nuclear decay. It's trying to become stable. So basically, the nucleus is crowded, way too many neutrons, and so it emits radiation in that process to become stable. Okay? And so when it tries to become stable, when it's trying to release energy, trying to get rid of particles inside the nucleus, all right, some things can happen. One, it can create a new element in the process. It can create a new form of the original isotope. And we call this process decaying. It is trying to become more stable. It is trying to find a happy medium of a good ratio between protons and neutrons inside that nucleus. So I'm not really big on scientists, memorizing them. I think all scientists are important. But they've made their contribution to science and moved on. So I really don't harp on knowing who scientists are, but I do think this one's important because of the accolades that she's had. So this right here is Marie Curie, or Madame Curie. And so she was a Polish scientist. And one very cool thing about her, and still to this day, to my knowledge, she is the only person that's ever done this. She has 2 Nobel Prizes in 2 different fields of science. She has one in chemistry and one in physics. No man or woman has ever done that in the history of science. So She's a pretty important woman when it comes to the scientific field. And so what makes her important is that she basically founded the field of nuclear chemistry. She noticed elements decayed. She noticed they were radioactive, they were emitting stuff. And she actually discovered two elements, radium and polonium. And you can see right there, polonium, the reason it's called polonium is because she was from Poland. But she basically discovered radiation. She is kind of the mother of all type of nuclear chemistry. So she's extremely important to the field of chemistry. So, moving on from there, all right, we said that elements become unstable and they decay, all right, because they're trying to become stable. So elements become stable, like I already told you guys, because they're trying to find a happy medium between a perfect ratio of protons and neutrons. Things become unstable when there are too many neutrons in the nucleus and it becomes too crowded. And so right here, here's the symbol. The symbol hasn't been around for long. This is not anything I'd quiz you on, but just thought you would find the history of it pretty interesting. Okay, so right here on this periodic table, all these elements that you see that are pinkish or purplish or orange here, these are all elements that are pretty much radioactive in nature. Like, we do not find them in stable forms. They will decay until they are stable. This is not anything you need to memorize. This is just elements here that are considered radioactive by nature. And as I've told you guys before, element 92, or past atomic number 92, which is uranium, everything past that point is man-made. It was made in a lab, and man made it. It's not something that's naturally found on Earth. Uranium 238 or 235 is probably the last elements that are naturally found. And uranium is found in an ore inside the Earth. So here are the three types of decay, or radiation that we call them. Okay, and so remember, when an atom has too many neutrons in the nucleus, it will go through nuclear decay. And so there's three types of nuclear decay for an element or an isotope to become stable. And so here are the three types. You have alpha, which is at the top here. You have beta, and you have gamma. This is a great slide because this tells you when this type of decay occurs, what is the product that comes out of the nucleus. And so this is actually going to be kind of some simple algebra here when we do this. Okay, so right here for alpha, it shows that when alpha decay occurs, we call this an alpha particle right here. But this is essentially the helium nucleus. It has two protons and two neutrons. And remember, if you look on the periodic table, the element that only has two protons is helium. Okay, you have hydrogen that has one, then you have helium that has two, and then lithium that have three. So this would be helium. But notice there's no electrons. It's literally just the nucleus of the atom. Two protons, two neutrons in that nucleus. When beta decays occurs, what happens is an electron is fired out of the nucleus. And we'll talk about that a little bit more. It's a little interesting. Gamma radiation is the most deadliest of all of them, and that is when gamma radiation is emitted. All right, that's a video, but we'll watch that later. Okay, so here's the types of radiation and what happens. Okay, this is a good slide to memorize right here. Alpha decay reduces the mass of the atom by 4 and the atomic number by 2, which we'll get into that in a second. Beta decay increases the atomic number, and gamma radiation just releases electromagnetic radiation, harmful radiation into the environment. Okay, so right here we have alpha decay. When alpha decays occurs, we have a nucleus that is unstable, and what happens is that helium particles emitted from the nucleus. When it does, it emits a mass of 4 out of it, so you would minus 4 from the mass, and it emits 2 protons from the nucleus, so we would reduce the atomic number by 2. Okay. Some things about this is when alpha decay occurs, alpha decay is really not the strongest type of radiation. It's fairly weak. And so really your skin or paper can block alpha radiation. It's not that harmful to us. But acute radiation exposure to it could be, but really not that deadly to us. It's not that bad for us to be exposed to. So here are some examples of alpha radiation. So all these elements left of the reaction symbol here shows us an element. So we have atomic number 92, element 238 as far as the mass. So this is uranium. And so if helium decay or alpha decay occurs, what you'll see is the mass of 4, because 2 protons and 2 neutrons get emitted from the nucleus. So a mass of 4 gets minus from the mass, and then 2 gets minus from the atomic number, which leads to an atomic number of 90. 2 minus 92 is 90. 4 minus 238 is 234. So we get to the element number 90 with a mass of 234. And if you look on your periodic table, if I'm not mistaken, element TH is thorium. So that shows right there uranium-238 decays to that. Okay. The next thing right here is beta decay. Beta decay is a little bit stronger than alpha. What happens here, and this is very interesting, when we don't really understand this phenomenon in science, but what happens is in beta decay, one of the neutrons randomly decides to turn into a proton. How does that happen? I can't answer that question. No scientist can answer that question, but that's what we know happens. So a neutron turns into a proton, and in that process, an electron gets emitted from the nucleus, gets ejected. All right. So the mass doesn't change. Remember, neutrons, protons weigh the same. So nothing changes for the mass, but what happens if you add one more proton, that means you're going to add one proton, 1 to the atomic number, so you're now going to change the identity of the element completely. So if you look here, we have carbon-14 with an atomic number of 6. If we add one proton to it, all right, the mass stays the same. Remember, neutrons, protons weigh the same. But if we add a proton to it, that means we have to increase the atomic number by 1, which leads to right here we would have the next element beside carbon, which is nitrogen. So this would be nitrogen-14. So this one's actually going up here. But the reason it's going up is because it's trying to get to a stable number of protons to neutron ratio. So right here are some examples of the equations. So right here we have potassium 42. Right here we know this is beta decay because an electron is getting fired out of the nucleus. And so since an electron is getting fired out of the nucleus, this is beta decay, and we should see from that 19 it should go to 20, and element number 20 should be calcium. But all of these show examples of that. Okay. Last one is gamma radiation. It's the most harmful to us. It is. Gamma radiation is extremely deadly to human beings. So we have to make sure we protect ourselves from it. However, gamma radiation is the easiest to remember. Gamma radiation doesn't really have a lot going on to it. Does not change the element's identity completely. It literally just emits radiation in the process of it decaying. Now, with gamma radiation, it can penetrate through a lot of things, but it can't penetrate through a concrete or lead wall. So concrete or lead can stop that radiation from penetrating surfaces, but lead can stop it. Okay. So there's gamma radiation. If you notice the identity of this element 27, I think element 27 is cobalt, going off the top of my head, but cobalt right here, cobalt 60, is not changing its identity from left to right. Okay. So right here is a good slide to look at that shows you the types of radiation and the penetrating ability of these. Alpha cannot penetrate paper. Beta can, but it cannot penetrate aluminum. Gamma can penetrate paper and aluminum, but cannot penetrate lead or concrete. So some good images here to look at and see which their penetrative ability is. Okay, so hopefully that was a good crash course for you guys. I know there'll be some questions tomorrow because we'll do some algebra with it, but just be prepared to bring those questions so we can work on it tomorrow. All right, see you guys.